Imagine if an evil scientist removed a person's brain and placed it in a vat full of nutrients, with the brain's nerve endings connected to a computer. In this case, if the computer could simulate biological electric signals that match human sensory systems through programs and input them correctly into the brain, then the brain would think it was living in a real world. However, everything it saw, heard, smelled, tasted, and touched would be virtual, simulated by the computer. This brain-in-a-vat thought experiment was proposed by philosopher Hilary Putnam in 1981 and subsequently sparked discussions about the question of whether the world is real. With advances in technology, humans have gained more understanding of the microscopic world, and scientists have reached a frightening conclusion through in-depth research. Various signs at the microscopic level indicate that humans may be living in a virtual world. There are mainly three aspects. First, quantum superposition states. In the microscopic world, a particle can exist in two or even multiple states simultaneously, such as an electron's spin being both up and down in a strange superimposed state, until the spin exhibits a specific direction when the electron is observed. I'm sure you've all heard of Schrödinger's cat, but you may not know that this thought experiment actually uses a both dead and alive cat to question the existence of quantum superposition states. However, subsequent research has shown that quantum superposition does exist objectively. As long as there is no observer, the states of microscopic particles are fuzzy, and as soon as they are observed, their states become determined. Why is this the case? If we use the virtual world to explain it, then we can assume that running a virtual world requires huge system resources, while the computer's capabilities are ultimately limited. To avoid wasting system resources, the program may blur unobserved areas until there is an observer. In fact, this is what happens in computer games we play normally too. To conserve system resources, the program will simplify details in areas of the game where there are no players, and this continues until players enter that area. Second, the double slit experiment. The double slit experiment was designed by scientists to study the wave-particle duality of microscopic particles. Wave-particle duality refers to how microscopic particles can have the dual properties of both waves and particles. The double slit experiment can be simply described as having a source, a plate with two narrow slits and a screen behind it to detect the microscopic particles. After electrons, photons, and other microscopic particles pass through the two slits, they will land on the screen behind. By analyzing the detected data, it can be determined whether the microscopic particles pass through the slits as waves or particles. For example, if interference fringes appear on the screen, it means the particles passed through the slits as waves. If not, then they passed through as particles. In the past, scientists have conducted the double slit experiment many times, and the results have invariably pointed to a strange conclusion. The way microscopic particles pass through the slits actually depends on whether they are being observed. Specifically, when passing through the slits, if observed, they will randomly pass through one slit as particles, but if unobserved, they will pass through both slits simultaneously as waves. In more in-depth research, scientists designed even more complex delayed-choice quantum eraser experiments based on the double-slit setup. However, the results showed that microscopic particles that have already passed through the slits seem able to determine, based on whether they were observed, which way they passed through the slits in the past. In other words, our current observations of microscopic particles appear to be able to influence the past states of the particles. As you can see, such experimental results are hard to comprehend, but if humans lived in a virtual world, it would be easy to explain, since such phenomena could be easily implemented with simple conditional statements in a program. Third, quantum entanglement. When two or more microscopic particles in quantum superposition states undergo particular interactions, they produce a mysterious connection called quantum entanglement between them. This connection persists even when they are separated and is a kind of instantaneous, distance-independent correlation. For example, suppose we have a pair of entangled electrons and send one to Mars while keeping the other on Earth. If we then observe the electron on Earth and cause its quantum superposition to collapse into a determined state, at that instant, the quantum state of the electron on Mars will also immediately collapse into a corresponding state. For instance, if we observe the electron on Earth to have upward spin, the one on Mars must have downward spin and vice versa. Einstein described quantum entanglement as spooky action at a distance, but believed there must be an as-yet undiscovered theory to explain it through classical physics. For example, if a pair of gloves is put in separate boxes, and we send one box to Mars while keeping the other on Earth, then if we open the box on Earth and observe the glove inside to be a right glove, we can immediately deduce the glove in the box on Mars must be a left glove and vice versa. But quantum mechanics holds that microscopic particles in quantum entanglement are in quantum superposition states until observed, meaning the gloves in the boxes are in a both left and right superposition before being observed. To determine who was right, physicist John Bell proposed Bell's inequality in 1964, mathematically deriving that if Einstein was correct, the inequality would hold. In 1981, physicists Alain Aspect, Philippe Grangier, and others began using entangled photons to test Bell's inequality. In the experiments, they used special crystals to produce entangled photon pairs and sent them to detectors at a distance. At the detectors, they randomly changed the angle of measuring the photon polarization and recorded each measurement. The results showed correlations between the entangled photons far exceeded the Bell inequality value, and the measurement results were random and unpredictable. This meant that Bell's inequality was violated. Einstein was wrong, and quantum entanglement really was spooky action at a distance. The experiment is considered one of the most important and influential in the history of quantum mechanics, laying the foundation for quantum information science and technology. In 2022, the scientists were awarded the Nobel Prize in Physics for their work. To this day, quantum entanglement remains an unsolved enigma in physics, but it makes sense if explained as a virtual world. We can think of quantum entanglement as the program referencing two or more pointers to the same object. In other words, entangled microscopic particles are just different manifestations of the same information unit displayed at different locations. The above is a reasonable conjecture by scientists about the true nature of the world. Does it make sense to you? That's all for today. If you enjoyed the content, remember to follow my channel.